So let's start today's lecture. So let me share the document camera first. Is that visible to you in the screen?
Yes, Professor.
Yep. Okay, great. So this is what we actually did so far. We actually did the root finding techniques and we saw how bisection method works, how regular false or the false method, fault position method works. And these are class of open methods for solving any equation. And we also saw how the open methods work like Newton's method and secant method. And we went over a specific example for the bisection method using the MATLAB coding exercise. Now, one of the open methods that we have not discussed is fixed point iteration method. So let's see what fixed point iteration methods is. So what the fixed point iteration method says that if you are given an equation to solve, let's say you are basically need to find a root, you want to find a value of x such that it satisfies f x equals 0. That's what we have been doing so far. So you basically try to find another function or rewrite this function in the form of x is equals to g of x. So I will just mention, or I will actually take some examples and see how this is actually followed. So what we have to do in fixed point iteration method is basically we rewrite the function or this equation in this form. And then we use this, we say that we do the iteration over x such that x of n plus 1, that is the n plus 1th iteration value, or the value of x for the next iteration is dependent on this function, which is g of x. So if I start with n equals 0 here, then what I will get is x of n, the first iteration, or after one iteration, the value of x will be g of x of 0, this is the initial guess or starting guess. Initial guess or starting guess. So like that, likewise, you will basically keep on doing several iterations. You say x of 2 is g of x of 1, x of 3 is g of x of 2, and so on and so forth. And you actually stop when you find that the difference between these two successive values of x or for successive iterations is close to the tolerance. So if I say that the difference between two successive values of x is less than the tolerance, then you actually stop the iteration. So this is how the fixed point iteration method works. So this is just the basic discussion of the algorithm. So let me know if you guys understand this part or not, or if you have any questions on this. Is everybody okay so far?
Yes, Professor.
Oh, yes, Professor.
Great, thank you. So let's take a specific example, what it actually says. So we will take this specific example. Yeah, there was any question, guys?
Yeah, I was wondering if you could explain it again, please.
Okay, so I will explain in the form of using example. So we will take example where we actually started this example and try to find the root of x, right? That's what we did in the last lecture, and we did that using bisection method. And we said that, okay, we'll start with this interval and which brackets a root. So here, this is basically a fixed point method is basically another solution technique, but it is an open method, class of open method. That means I do not need to know the bracket. I can start at any point. Now there are some conditions on at what point you can start. We will discuss that. But let's first take this example, which is given as e of x minus 2x equals to 2. So what is the function fx is basically can be written as e of x minus 2x minus 2 equals to 2. This is your f of x. And you need to find the value of x such that f of x equals to 0, isn't it? Are you guys with me?
Yes.
Yeah. So we need to, in fixed point iteration method, we need to map this or basically rewrite this function fx in the form of a gx, which is this form. So how can I transform this equation in this form? So what I can do is I can write it as x equals e of x minus 2 divided by 2. the same equation as this. Yeah, you guys with me?
Yes.
Yeah, and this is what your g of x is, new g of x is. This is basically the same form as this. So what I did, I actually start with this, or this is my function f of x equals 0. That's basically the function for which I need to find the root, or I need to find the value of x which satisfies this equation. Now, instead of using this function, I rewrite this function in the form that x equals to gx, where g of x is nothing but is this specific function. Are you guys with me, guys? Yeah.
Yes,
Now,
Professor.
once you have this, what you do thereafter is just use this specific, very simple iterative root finding technique. Iterative root finding technique means you assume a specific value of x, which is your initial x. And for the next iteration, you will get the value of x like this. So you will get x of n is equals to e of x0 minus 2 divided by 2. And what is 0? X0? X0 is the starting guess. So let's say I start with this.
Professor, can you move the paper up, please? Thank you.
Sure. Starting guess. So I started with this x of x is equals to g of x. And then but I said that if I have to solve for x, the fixed point iteration method says you can solve it in an iterative form, where you can say that you can start with the current assumption or current value of x, and the next value of, or the next iteration of x, you can solve this equation and you can find the next value of x, or you can find the value of x for the next iteration. So let's say I start with x0 is equals to 0. Now I take this as a guess. We will come to this point that why I took x0 is equals to 0. Why not x0 equals to 2 or something else? So let's say I take x0 is equals to 0. Now you guys have to help me to find out what will be x1 if x0 is 0. It will be 1 minus 2 divided by 2, which is minus half. It is minus 0.5, isn't it? Yeah.
Yes.
X2 would be e of x1 minus 2 divided by 2, where x1 is minus 0.5. Now you have to help me here. What will be x2?
Point 36.
How much?
0.36.
Negative or positive, is it?
Positive.
Positive. And now if you have to keep on doing it, let's say we will keep on doing it till till 5. So x3, x4, x5. Can you find the values of x3, x4, and x5? Where x3 will be e of x2 minus 2, x4 will be e of x3 minus 2 by 2, and so on and so forth. So can you guys solve that and let me know what the values would be?
Negative 0.28.
Negative 0.28. Okay.
Excuse me. For X2, I have negative
6.9.
0.69. Yeah, 0.69.
Yeah, I got the same thing.
Okay, guys, you have to help me to see what is the correct value here. So what is the x2?
Yeah, I also got negative 0.69.
Negative 0.69. Okay. Please correct me here. And what is x3 then?
Negative 0.75.
Negative 0.75. What will be x4?
Negative 0.764.
How much you say?
Negative 0.76.
Okay. And x5, the last one?
Negative 0.767.
Okay. So as you are seeing now, as you keep on doing this, I mean, I'm not I'm not saying whether the values are correct or not. I'm trusting you guys on the calculations, but you guys will see that as you keep on going, you will see that the values are basically getting more and more, the successive values of x are basically getting more and more closer towards each other. So as you go on x6, 7, 8, 9, 10th iteration, you will find that it will be the x that you can basically get, you can see the stopping criteria will be satisfied, and that will be the root of that equation. Does that make sense?
Yes.
Yes, Professor.
Okay, great.
Professor, quick question. So that will be given the value on the right of the sign, where it says the absolute value of the difference between xn plus 1 and
This is a tolerance, and you can always say the tolerance is basically very small number, which is very, I mean, you can say by default, you can take that number. For any tolerance, whenever we talk about tolerance, it is just a default very small number. Let's say this.
Okay, thank you.
Yeah, welcome. Now, can I ask you guys to do me a favor and say that what is negative point, if you substitute negative 0.767 on this, what do you get?
Negative 1.43 10 to the negative 3.
How much you get, sorry? If you substitute x as negative 0.767.
So it's negative 1.43 times 10 to the negative 3.
Okay, let me say if you substitute this value in f of x.
I got a value closer to 0.
Yeah, so what is that value? I'm just interested in knowing.
Negative 1.59 times 10 to the negative third.
Great. Now, I'm not sure if you remembered this. Did we solve this equation using bisection method in the last lecture?
Yeah, we did.
Yes.
And what the value of x did you get in that using bisection method?
It was like, I don't know.
1 point something, 76787.
Yeah, I think it was like around 1.6 or 1.7, somewhere around there.
Around there, right?
It was 1.6783.
Yeah, perfect. So that was around 1.6783. That was using bisection method. You were getting some number, right? 1.67, some number, which I don't remember now, but it was some number, okay? Now, when we are using bisection method, we are starting with this bracketing with this interval, and we said that the root will lie within that interval. And when we did the bisection method, we actually found that the value of x was close to around this value, this range. But when I use the same equation and I'm using the same function, what I'm actually doing is I am using now fixed point iteration, basically an open method, which is a class of method where you do not need to, a class of open method, which is a class of method which does not need a bracket or interval. And I start with this guess. And with that guess, what I'm getting the value which is close to negative 0.676, which is basically another root of this equation, basically, isn't it? So you're seeing what I'm doing here? I'm getting. So if I start with x naught is equals to 0, I get this. Now, I would like you to basically repeat the same step, but instead of x naught equals to 0, I will ask you to do for x naught equals 2. What do you get as a starting guess? If you say x naught equals to 2, what do you get as x1, x2, x3, x4, x5? So you can do that calculation and tell me what will be x5. And before you actually do that calculation, I do not have the calculator, so I'm just asking you guys to do that. So can you tell me what this number looks like? Half of E2. What is this number? what this number basically is equals to 1/2, or basically half times e raised to the power 2 exponential of 2.
I got 3.6945.
945. Okay. So having done that, we will come back to this, why I asked you to calculate this, but you can now proceed on this calculation where x0 equals to 2, which is a starting guess, and calculate successive values of x1, x2, x3, x4, and x5. And let me know what is x5 and what is your function value at that point, at that x5. So you calculate x1, then calculate x2, x3, x4, and x5, and let me know what that value is and what is the function value at that point. So what is x5 and what is function value at x5 when x0 equals 2? So can anybody tell me what your x5 is coming out to be?
Seems to be diverging.
Yeah, so it will diverge. So what is
Yeah.
X4 was too big. I don't think the calculator couldn't handle. X3 is 299.7.
Okay, okay. So basically you are seeing it is basically divergent. It's a very big number, right?
Yes.
Big number. And it is basically again big number, basically moving towards infinity, isn't it?
Yes.
Yeah. And last one, what is E1 and half? What is this value?
I got 1.35 and
1.5.
1.
Okay, and what is half of E of 0.5?
0.82.
0.82. Okay. And last exercise. So we will actually stop with these calculations. Start with x0 is equal to 0.5 and let me know what is x5 coming out to. That's the last. I
Start
promise.
with which one?
We'll start with this. x0 is equals to 0.5. I will not ask you for more computations after this. So if you start with x0 equals to 0.5, what do you get actually?
I got negative 0.1756.
No, I'm asking for x5. What will be x5?
Negative 0.765.
Great. Great. So we will stop at that and we will now start discussing why we were doing all this calculation. What is the meaning of that? So let me actually start with this. So again, we will start with this fixed point iteration method. And by now we know, just give me a second. Yeah, by now we know that what the method says, that if you transform this function, rewrite this function in this form, and then you use successive iteration techniques, solving techniques where successive values of x for successive iterations are solved by using this form, then you actually basically get to know the root of the equation or the value of x, which is basically called as a fixed point of g of x, and you stop at the iteration. I stop at the iteration number where this specific condition is hold true, where the successive values of x is less than the threshold value. So what essentially this method is doing, it is basically trying to, so instead of, let's say, if you have a function of fx equals 0, so let's say this is your f of x, and you want to find a root where f of x equals 0, what this method is doing, it is trying to solve the intersection of two functions. Basically, when we are doing fixed point iteration method, we are writing f of x equals 0 as x of x equals g of x. So what we are trying to solve is we are trying to find the intersection of these two functions. So one is this, which is straight line. Another one is this function. So y is equals to x is a straight line. And another function is basically, let's say this is of g of x. Y equals g of x. This is y and this is y. This is x. So what it is trying to do, this method is trying to transform this specific function in this form, where it is now trying to solve the intersection of a straight line with another function, which is g of x. So wherever the intersection happens, that intersection is basically the root of the function. So that is what this method is doing. That is the basic abstraction or basic idea behind, or basic philosophy behind fixed point iteration technique. Now, since we know that this is an open method, so basically we do not know where this root will lie, whether this root will lie at x equals 0 or x equals 1 or 2 or wherever that is. We do not know where this root lies. So we actually start with a specific value of my x as a starting guess. So if I take a specific starting guess, I will find, so the question arises that can any value of starting guess which should help me to solve or to find the root of the function, or in other words, when I say root of, in other words, what I'm trying to say here is when I'm solving this equation, then we are saying that our stopping criteria is xn plus 1 minus xn should less threshold or should be less than the tolerance. Now this is only true when this sequence is converging. This is true for converging. True only if the sequence is converging or the iterations are converging. Sequence is converging. Do you see what I'm saying here? So when you actually start with x naught equals to 0, you will see, you found out that if I go back to this page sheet, so you start with this x naught equals to 0, and you see that at a successive x1 and x2, it is basically closing in towards the actual root of the equation, where fx equals 0 or x of, or the successive values of x are basically becoming closer and closer together. They are converging to one specific number. Do you see what I'm saying here, guys?
Yes.
Yes.
Yeah. Now, at the same time, if I change the starting guess from x naught equals to 2 to, x naught equals to 0 to x naught equals to 2, you just found out that the successive values of x are not converging. This relationship will never be satisfied because successive values of x are basically getting increasing and function value is becoming infinity. So we are basically diverging. We are not able to converge towards our fixed root. So depending on the starting guess, you can have either convergence or divergence. So what is the condition? How do we know that the starting guess should we take or should we choose? So to do that, what you have to do is the condition for convergence is, for this method is that if you take the derivative of g of x and take its absolute value and make it less than 1, then for any value, for x is equals to whatever starting value, then you can assume that is basically a sufficient condition for convergence. Not a necessary, but sufficient condition for convergence. So that is what I have been asking you to do that. So let me rewrite that function. I was basically using this function where g of x was given by this specific form. Now, if I take g prime of x, what do I get? I get half e of x. Now, this is what I actually get for g prime x. Now, if I select g prime of x at x equals 0, I get that as 1/2, which is 0.5, which is less than 1. So if I take x equals to 0 as a starting guess, I can guarantee, not with 100%, but 99.999, whatever percentage is, that my sequence will converge. So I start with x is equals to 0. That is my starting guess. And since this satisfies this condition, that is g prime of x at the starting value is less than 1, then I am pretty sure that my sequence will converge. The same thing was happening when I was selecting x equals to 1 and x equals to 2. When I select x equals to 1 or x not equals to 1, let's say, I am getting g prime of x at x not equals to 1 is greater than 1. That's what you told me, that it is around, basically it was 1.35. Somebody told me that is 1.35. It is greater than 1. Similarly, if it was x not equals to 2, g prime of x is x not equals to 2 is around 3.6945. Basically, what I'm basically referencing is these numbers. When I was asking you to calculate this number, this is essentially nothing but I was asking you to calculate this g prime of x, which is half of ex. So at x equals to 2, I basically was asking you to calculate this number. And this number turns out to be 3.6945, which is basically greater than 1. And when you start with this, x not equals to 2, you see that this is basically diverging. Did you see what I'm saying, guys? Yeah?
Yes, Professor.
Yeah.
Yes.
And
Yes,
when I ask you to calculate this, then also you give me a number which is greater than 1. So I do not ask you to do the calculation with 1. Then I changed it to 0.5 and somebody told me it is 0.82. That is less than 1. So I asked you to redo the calculation 0.5, and again it was basically converging towards the same number which you are actually getting it when you start with x not equals to 0. Do you see what I'm saying? So even if the starting guess is different, so what you are seeing here, that it need not be, the starting guess need not be a specific value 0. It can be -1, -2, -3, -infinity, any number, as long as this condition is satisfied. That is g prime of x at the starting value should be less than 1. G prime of x at the starting value should be less than 1. As long as this condition is satisfied, you can select any starting value of x and you will see that the sequence will converge and converge to your root. But the moment this condition is not satisfied, then you are basically going to diverge. So that is what you are going to see, divergence.
That's a quick question. Will it always converge to this root?
Yeah, so that's a good question. So that was basically the thing I was trying with different values of x naught. And eventually we actually saw that it is always converging to this root. It is never going to 1.678 basically. So it was not basically g of x is diverging. So this method will never actually, for the guesses that we are taking, we are never reaching to this specific value or specific root. So this specific technique only gives you one root, not the other one. So you basically have to try different methods to basically see whether you are getting this root or not. Does that make sense?
You said it only gives you one root, right?
It may give you different roots as long as that you are basically satisfying this specific condition. Now to get 1.678, I was trying, so near that root, so 1.678, if you select 1.5 as a starting guess, 2 as a starting guess, 3 as a starting guess, you are seeing that that is always going to be diverging. So this method is never going to give you, because of the specific condition that g prime of x is not less than 1. So basically, only this specific example for this specific method will show you that you will never be able to go to that near, will basically reach this root because of the specific condition. Does that make sense? Yeah.
Yeah, that makes sense.
So just to make sure that this method does not give you one root, but more than one root, what we basically have to do is, there is not one way of writing x of x equals to g of x. So for example, I am writing this form x equals to g of, there is other way, other method as well to basically write x as g of x. For example, if I take this form and I use this equation here, e of x minus 2x minus 2 equals to 0. And I'm writing it e of x is equals to 2x plus 1. And I take natural logarithm on both sides. Taking natural logarithm on both sides, what do I get is x of ln of e, natural logarithm of e, that is 1, and natural logarithm of 2 plus ln x plus 1. And this is x is equals to ln 2 plus ln natural logarithm of x plus 1. So I can also write my g of x. So this is my new g of x. Basically, I'm using the same function, f of x equals 0. And I'm writing this as this form. And this is again in the same form that we actually started with, but it is a different function now, isn't it? Are you guys with me?
Yeah.
Yeah. So either you can write it as this form from the same function, or I am basically trying to write it in this form. I just use a separate way that I am writing my x of g of x. Now, if I take the g prime of x, what I actually get is 1 over x plus 1, right? G prime of x, or derivative of g of x, g2 of x, isn't it? If I take the derivative with respect to x, I get this. And if I say that, okay, what is g2 derivative of x at x equals 2? And you will say that it is 1 over 2 plus 1, which is 1 over 3, which is less than 1. So if you select g2x, g of x as this function, and now select x equals to 2 or x not equals to 2, and then you can find successive values of x. Can you tell me what you are getting?
Quick question. Why is it g2 of x? Isn't it just g of x?
It is, but I'm just saying that this is 1 and this is 2. There is another one basically.
Oh, okay. Okay, thank you.
Yeah, that's it. So what I'm asking you guys is to do the same calculations, but now you are using this function as g of x, and instead of x naught, you are in place of x naught, you are using 2. So xn plus 1, this is x1, it will be ln2 plus natural logarithm of 3. So that's how you will actually get. So can you tell me what are you getting values? What is x1 you are getting? What is x1, guys?
1.79.
1.68.
1 point
For x1, it's 1.79.
79. What is x2?
1.71.
And what is x5?
1.68.
1.68. And now you see, basically you are going to get this root. You see what I'm saying? Now, if you actually go to different x6, x7, x8, x9, and x10, you see basically it is converging towards this specific number, which is what you actually got using bisection method. Did you see, guys, what I'm saying here?
Yeah.
Yeah.
So essentially, the question that you guys asked is, so can we always, will this method always give you one root? So it depends on the nature of your g of x. That's how you actually transform. So for this specific g of x, you, no matter what you do, you are always getting this root. To get different root, you need to use different g of x. So you need to rewrite in separate, in another form. That's what I did. I rewrite this equation, same equation in another form, which is this. And now when I select a value of x naught as 2 or any other number, because I know that g prime of x is less than 1, so I'm going to converge. So I start with this, and then you will see that it is slowly converging towards your another root of this function. So the fixed point iteration method works by first transforming your function in this form x of g of x, and then you use a starting value such that g prime of x should be less than 1 at that starting value, and then you keep on doing the iteration. And that's how you basically converge towards root. Now, same g of x may not give you all the roots, so you may have to use different g of x to get different roots of that, different roots. That's what we actually saw here. Does it make sense, guys?
Yeah. So we're rewriting g of x in a different form to verify that the root is correct?
No, not to verify the root is correct, but to get another root of the same equation, if something like that exists.
I see.
For example, I don't know how many roots of this equation actually exist. So unless I plot this function, I do not know. So I do not know whether there are 1 root, 2 roots, 3 roots, 4 roots, how many roots of this equation exist. So what I'm basically using, I am using different methods and different techniques to find different roots of this equation. Now, what these methods we have learned so far are nothing but different tools we have. So we sometimes bisection method is a specific tool. If you know that a specific interval exists for the root, then you can use bracketing methods. You can use bisection method or false position method. Or if you do not have any information about the interval of the root, you can start with open methods. You can do Newton method, secant method, fixed point method, any technique that you think will help you to get the root. So these are just the tools or techniques that will help you to get the roots of the equation. You can select any one. Each one of them has a pros and cons. I mean, if you go into the depth of the individual techniques, you will get to know about it. But what you be actually learning here, what are the different techniques by which MATLAB actually solves it for you, solves this function, solves a root for this function for you. So MATLAB basically selects one of these methods and gives you the different roots that exist for a specific function. So in practice, in other words, in practice, you probably are not, if you have to solve for a root of the function, you are probably going to use MATLAB, but at the same time, you know that it is basically on the background, it basically are using one of these techniques to actually solving the roots. Does it make sense?
Yeah, that makes sense.
Any questions, guys, so far? Okay, if not, then basically I'm going to, let's say, go through once again what we have seen so far. We have covered bisection method, we have covered false position method, which are bracketing methods, and we have covered open methods. Open methods, there are 3 techniques: Newton's method, secant method, and fixed point. Today, we have basically gone over the fixed point method, where the fixed point method works, where you don't need to worry about a derivative of the function at different points, but you just need to calculate derivative only once. only once basically means to check whether the starting point is going to converge or not. That's only where you need to take the derivative of the function. So that is what how the fixed point method is different from this Newton method and secant method. In Newton method, if you remember, you basically take the derivative of a function for every iteration. In secant method, we are not taking a derivative, but we are taking a derivative using some numerical technique by using the last 2 points and finding a tangent line through those last 2 points. Now, what I'm saying may be making sense to you or may not be making sense to you, depending on how much you are going through your notes or revising your notes. So just on another note, what you guys have to do now, from now onwards, you have to start practicing problems, unsolved problems from your textbook. Now, I'm not going to give you regular homework problems that will be graded, but I will actually let you know that this is what now you have to start practicing on your own using the unsolved problems that will give you some insight about these techniques. Now, what I will be going to give you the homeworks are basically specific homeworks that will have questions combining all the different techniques, all the different methods together, and probably will ask you to compare how each method is working versus how the different methods are basically converging or not converging, or what is the behavior, or what is the difference when you use different methods or techniques for a given problem. So the homework that you will be assigned formally will be graded and will be assigned to you, but you please do not wait for those homework problems to be assigned to start working on the exercises. So as soon as we cover a specific topic, I would request you guys to please go through the unsolved problems in your textbook and start practicing it. And that will give you a more good hands-on insight, or give you more better insight about how to solve or how these techniques work. Does that make sense, guys?
Yes, Professor.
Yeah. So having said that, coming back to the fixed point method. So here we are not taking derivative at every iteration. So we are just taking derivative at the very beginning. And that's what we did to make sure that our starting value is less than 1 or not. So that is what we are doing only once. And thereafter, it is very easier method where you are doing successive iteration, or successive values of x's are basically solved using function evaluation of a g of x, where g of x is basically rewriting the function fx in this form. And to make sure that the g of x is actually converging, you make sure that the g prime of x, the derivative of g of x at that starting value, is less than 1. So that is what you are trying to do. So that basically completes our discussion on fixed point iteration technique. Let me know if you guys have any questions or something that you are not understanding at this point.
Yes, Professor, you said that you mentioned that you asked us to practice examples from the book, and you meant calculating by hand, not MATLAB. Is that correct?
No, from now onwards, use MATLAB. So whenever you are doing some derivations, do it by hand. But whenever you are basically doing some complex algebra or complex calculations, just use MATLAB. So when I say MATLAB, don't use MATLAB inbuilt functions, but try to write your own code. So as I will show you in the next lecture how to go through basically we saw one code or writing bisection method. Similarly, you can implement any method in your code or in a MATLAB, or there are existing codes in your textbook. You can just copy them and you can create the functions and you can solve and practice those specific problems.
I checked the codes in the book. They don't follow the same steps that you did. So I was wondering.
Which code does not follow the same step?
Just checking the exercises that from the book.
Okay, we will go through that in the next lecture. We will see one day example and I will show you what you need to do. So we will actually go through one specific example using MATLAB. Okay.